Welcome to another module in this massive open online course. So we've looked at various optimization problems sort of informally. What we're going to do in this module and the subsequent, a few of the subsequent modules, is to basically set out or basically lay down the sort of formal framework to basically state to basically for the formulation of a convex optimization problem. All right. So let us discuss. Let us begin our discussion, so as to speak, on the formal framework of a convex optimization. Of a convex optimization problem. And now a convex optimization problem, as we have seen in the standard form, alright, this can be thought of as a canonical form or the standard form of a convex optimization problem. Or a textbook convex optimization problem can be stated as follows, that is, you minimize, or this can also be sometimes written as min. In fact, we will frequently simply write it as min period, which means minimize an objective function. All right, this is basically can be objective function of vector, can be objective function of a scalar. So g naught of x bar, subject to some constraints like we have seen so far, or s dot d dot or t dot subject, and these constraints can be gi of, you can have any number of constraints, g of x bar less than or equal to 0. And now this objective function g naught has to be, this has to be a convex. Remember, for a convex optimization problem, this objective function has to be convex. I can have these constraints, each of these constraint also is convex, it is a convex function. I have I equals 1 to up to L constraints, and in addition I can have equality constraints gj tilde of x bar equals 0, and these have to be, for instance, j equals 1 to up to m, and these have to be affine constraints. The equality constraints have to be affine in nature. Which basically implies that they are hyperplanes. So you have to have constraints of the form aj bar transpose x bar equals bj. So these are affine constraints, or basically these are hyperplanes. Okay, so the equality constraints, the inequality constraints can simply be convex functions, and of course the objective itself is a convex function. Right. So this is a standard form of a convex optimization problem. So you can think of this as a standard form you can think of this as a standard form convex optimization problem. And what is the advantage of a convex optimization problem that we have so formulated? And the important advantage, as you might already know, for a convex optimization problem is the following, that is, when you look at a convex objective function and you minimize it, the minimizer for, so this is your convex objective, and the minimizer is, or the optimum value is unique, the minimizer need not be unique, but the optimal value or you can think of this as the minimum or optimal value is unique. Okay. Now, as against if it is non-convex, for instance, all right. So, if it is non-convex, now what happens here is you have the concept of what is known as a for instance, if you look at this here, this is also, it appears like a minimum, but this is only minimum locally, that is in a local neighborhood, in a certain neighborhood. It is, for instance, if you look at this neighborhood, it is the minimum, but it is not the minimum globally. The global minimum, that is minimum over the entire domain, is this. So, this you have the concept of a global minimum, and this is the local minimum, okay, when the objective is non convex. However, here local minimum, any local minimum is the global minimum. Okay. So, that is the advantage of convex optimization, that is any local minimum is global minimum, or here in non-convex there can be very many local minima and only one global minimum, alright. So, the problem is that the algorithms, that is the optimization algorithms that you employ, can get trapped in this. So, they can get trapped in this local minima and they can yield spurious solutions which are not actually the minimum, which are not actually the optimal values of the objective function. So, for non-convex you have this problem that for non-convex the optimization routine or optimization algorithm is trapped, that is the terminology used frequently, trapped in local minima, implies there is a, you have spurious solutions or non-optimal. Or non-optimal solutions, and this is precisely because there is only a, whatever is a local minimum for a convex optimal objective function is a global, or a convex optimization problem is a global minimum. So, this problem of spurious minima or local, getting trapped in local minima is entirely avoided by a convex optimization problem. So, this problem does not, and that is the advantage of a convex optimization. This problem does not arise in a convex this problem does not arise in a convex optimization problem, and that is the advantage of the convex optimization framework. And that is the advantage of the convex optimization framework. Okay, that the algorithm, because there are no local minima, all right, you only have global minima, so the algorithm does not get trapped in local minima. Now, a related form, in fact, something convenient reformulation you can think of. It as a convenient reformulation of a convex optimization is what is known as the epigraph form, which I am going to describe shortly. So, a convex optimization problem can be recast in what is known as its epigraph form. And that is the following thing, That is, remember we said you have a convex optimization problem, minimize the optimization objective G naught x bar subject to the constraints G f x bar less than or equal to 0 for 1 less than or equal to I less than or equal to L, and G j tilde x bar, these are affine constraints, or I can write this directly as in fact A j bar x bar equals B j, A j bar transpose x bar. These are hyperplanes, 1 less than or equal to j less than or equal to m. And now I can write this in epigraph. So, this can be equivalently expressed as follows. What I am going to do is I am going to introduce an additional variable optimization. So, this optimization here is with respect to x bar. I am going to introduce an additional optimization variable t, that is minimize x bar comma t. Now, I am going to minimize t, and in the constraint now I am going to add an additional constraint, that is g naught of x bar less than or equal to t. Okay. And the rest of the constraints remain the same, that is j of x bar less than or equal to 0, I equals 1 to up to L, and Aj transpose x bar equals Bj, j equals 1 to up to m. So, these constraints remain same. So, my optimization objective now becomes simply T. Optimization objective simply becomes T, and I have one additional constraint. And the point is that this is still a convex optimization problem, because if you look at this optimization, this is simply linear, this is simply T. So, this is convex, is simply function of T, this is convex, and we already said the optimization objective G naught x bar is a convex function, right. So, G naught x bar less than or equal to T, that is a convex constraint, alright, convex function less than or equal to T, alright. So, that is allowed in a convex optimization problem. So, this is a convex constraint, and therefore, this is still a convex optimization problem. It is a very simple and elegant reformulation that simplifies many complex convex optimization problems. So, this modified optimization problem, this is still convex, and it yields the same solution, that is the solution x bar of this problem, optimal value, that is optimal solution x bar of the second problem of this of the second problem is the same as the optimal value x bar that you obtain from the first problem. However, in the second problem you are optimizing both with respect to x bar and t, okay, and this is termed as the epigraph form. This is termed as the epigraph form of the problem, okay. And in the epigraph form of the problem, and as I already told you, epigraph form, it is helpful in recasting this convex optimization problem in a more interesting or intuitive form. So, the epigraph form, the advantage of epigraph form is basically it is helpful in recasting convex optimization problems. In more in a more interesting or intuitive form. In a more interesting or intuitive form. And let us look at a simple example to understand this better. To understand this better, let us look at a simple example for this epigraph form, and a simple example can be the following thing, which is basically I want to, so let us consider this problem, minimize, sometimes you can even, frequently it is also written even omitting this period after min. So, this stands for minimize, minimize norm x bar the infinity norm subject to the constraint. Let us say there is some constraint, that is x bar belongs to the set S, that is it is a combination of linear and affine constraint. Let us say some constraint, this x bar must belong to this set S, which is basically a convex set. Okay. I am not too worried about these constraints. So, this is our, now look at this, if the set is convex, so the constraints are convex, and remember this is a norm, infinite norm, this is a convex norm. So, this objective, this is a convex objective, okay, as a convex objective, and therefore, this is in fact a convex optimization problem. Okay. Now, this is in fact a convex optimization problem, and now what we want to formulate is the equivalent epigraph form. We want to formulate the equivalent epigraph form, and that can be derived as follows. So, I can write this as the epigraph form minimize, remember the epigraph form is straightforward, minimize t, objective function is always t, subject to the objective, original objective, of course this minimization is over x bar comma t, norm x bar infinity is less than or equal to t, and the original constraints remain, that is x bar belongs to this set S. Okay. So, this is the epigraph form. Now, I can modify it slightly. Now, if you look at this norm of x bar infinity, let us say x bar is a vector, okay, n dimensional vector. Norm x bar infinity is nothing but, the infinite norm is nothing but maximum of magnitude x1 comma magnitude x2 magnitude xn, and when we say infinity norm is less than or equal to t. So, this implies, so this constraint here, this basically implies that the maximum of magnitude of x1 up to magnitude of xn, this is less than or equal to t. Now, the maximum of n components or n quantities is less than or equal to t, that is possible only if each of the quantities is less than or equal to t. So, this in turn now leads to something interesting. So, this implies that magnitude x1 less than or equal to t, magnitude x2 less than or equal to t, so on and so forth, magnitude xn less than or equal to t. Now, magnitude x1 less than or equal to t, this implies that minus t less than or equal to x1 less than or equal to t. Similarly, magnitude x2 less than or equal to t implies minus t less than or equal to x2 less than or equal to t, and so on. Magnitude xn less than or equal to t implies minus t less than or equal to xn less than or equal to t. And therefore, now the optimization problem above, therefore, the epigraph form therefore, the epigraph form can be simplified as minimize of t, minimize with respect to t, subject to minus t less than or equal to each xi. In fact, let me just write it explicitly to illustrate it. Minus t less than or equal to x1 less than or equal to t, minus t less than or equal to x2 less than or equal to t, and so on, minus t less than or equal to xn less than or equal to t, and the original constraints are always there, that is x bar belongs to this set S, which is the original constraint, and this is something that is more intuitive. Okay. And these are, in fact, if you look at these are some sort of box constraints. You can think of this constraints x bar to lie in a box of dimensions 2t. In fact, that is what you will see. If you consider a 2-dimensional scenario, that means your x1. So, if this is your x1 and this is your x2, so x1 has to lie between minus t and t, x2 has to lie between t and minus t. So, that effectively limits your area, that is your x1 x2 has to lie in this. So, this is the box. Okay. So, this is the box in which your x1 x2 has to lie, alright. So, this is basically your, you can think of this as your box constraint, alright. So, basically introduces a box constraint for the original optimization. So, introduces a box constraint, you can say that it introduces a box constraint for the original optimization problem. Okay, so it sort of introduces a box constraint for the original optimization problem, and this is something that is it gives you an interesting, either gives you better intuition or it also gives you an interesting interpretation for the original optimization problem, which is in fact an identical, it is an equivalent optimization problem, but it's sort of opaque. Alright, one can, it's not amenable to derive insights. Alright, so then this modified optimization problem is something that's more interesting. And it is easy to interpret and probably also analyze sort of without using rigorous analytical tools, sort of analyze it more or analyze or interpret it sort of simply by looking at the optimization problem. Alright. So, this is an important, in fact, one can use this, and we are going to also use it from time to time to simplify or recast optimization problems. Alright. So, we will stop here and continue in the subsequent modules. Thank you very much.